Hello guys, welcome back. I am your friend in Excel. Today we are going to learn the ratios, rates, and proportions.
We've got some apples here and we've got some oranges. And what I want to think about is what is the ratio? What is the ratio of apples to oranges? And to clarify what we're even talking about, a ratio is giving us the relationship between quantities of two different things. So there's a couple of ways that we can specify this. We can literally count the number of apples, 1, 2, 3, 4, 5, 6. So we have 6 apples, and we could say the ratio is going to be 6 to, and then how many oranges do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. It is 6 to 9. Ratio of apples to oranges is 6 to 9. And you could use different notation. You could also write it this way. 6 to, you would still read it as the ratio as being 6 to 9. But we don't have to just satisfy us with this, because one way to think about ratios, especially if we're thinking about apples to oranges, is how many apples do we have for a certain number of oranges? And when you think about it that way, we can actually reduce these numbers, as you might have already thought about. Both 6 and 9 are divisible by 3. So just how like we can reduce fractions, we can also reduce ratios. So if you divide 6 and 9 both by 3, 6 divided by 3 is 2. 6 divided by 3 is 2. And 9 divided by 3 is 3. So we could also say that the ratio of apples to oranges is 2 to 3. Or if we want to use this notation, 2 to 3. 2 to 3. Now, does that make sense? Well, look, we divided each of these groups into 3. So one way to think about it, so if you divide this whole total into 3 groups, so one group, two groups, and 3 equal groups, we see that in each of those groups, for every 2 apples, we have 3 oranges. 2 apples, we have 3 oranges. 2 apples, we have 3 oranges. So, once again, the ratio of apples to oranges, for every 2 apples, we have 3 oranges. Well, we could think about things the other way around as well. We could also think about what is the ratio. Ratio of oranges to apples. And here we would essentially switch the numbers. The ratio of oranges to apples. Notice, up here we said apples to oranges, which is 6 to 9, or 2 to 3 if we reduce them. And here we're going to say the ratio of oranges to apples. So we've swapped these two, and so we're going to swap the numbers. Here we have 9 oranges for every 6 apples. So we could say the ratio is going to be 9 to 6. The ratio is 9 to 6. Or if we want to reduce it, for every 3 oranges, so we're going to divide this by 3. So for every 3 oranges, we are going to have 2 apples. So notice, this is just exactly what we had up here. But when we had apples to oranges, it was 6 to 9, 6 apples for every 9 oranges. And now when it's oranges to apples, we say it's 9 to 6. 9 oranges for every 6 apples. Or we could say for every 3 oranges, we have exactly 2 apples. 6. 9.
Okay, let me re-explain the concept of ratio. It just represents a relationship between two kind of things, and for here it's the apple vs the let's say oranges, and for this ratio, it means that for every 2 apples that we get a corresponding 3 oranges. It shows the relationship of two different things. Or sometimes we can even do more. For example, we can write more, let's say this kind of symbol to represent more relationship or between more different things. Let's have a look at the application for the ratio.
We are told that a baker uses 8 cups of flour to make 1 batch of muffins for his bakery. Complete the table for the given ratio. So they're saying that for every batch, he needs 8 cups of flour, or he needs 8 cups of flour for every batch. So if he had 2 batches, how many cups of flour would that be? Pause the video and try to figure it out. Well, if he has twice as many batches, he's going to have twice the number of flour. So instead of 8, it would be 16 cups of flour. And if he had 3 times the number of batches, it would be 3 times the number of cups of flour. So instead of 8, it would be 8 times 3, or 24. Now down here, they say plot the ordered pairs x, y from the table on the following graph. So we want to graph 1 batch, 8 cups, 2 batches, 16 cups, 3 batches, 24. So let's do that. Okay, so right here, this I'm assuming on the horizontal axis, that is our batches. And then on our vertical axis is cups of flour. So for every batch, we need 8 cups of flour. So one batch is 8 right over here, 5, 6, 7, 8. And then for 2 batches, we're going to need 16 cups of flour. So that right over there, that's 16. And then for 3 batches, we are going to need 24 cups of flour. And that actually goes slightly off of our screen. 3 batches, we are going to have to bring that to 24, which is right here. And I can see the 25 right above. And what you'll see, because the ratio between our batches and our flour are constant, that all of these points, you could connect them all with one straight line because we have a fixed ratio. Every time we move 1 to the right, we're going to move 8 up. Every time we add another batch, we're going to have 8 more flour. Every time we add a batch, 8 more flour. Let's do another example. Here we're told Drew earns money washing cars for his neighbors on the weekend. Drew charges a set rate for each car he washes. Points on the following coordinate plane show how much Drew charges for 2, 5, and 8 cars. See what's going on. So when he washes 2 cars, he looks like he charges $15. When he washes 5 cars, it looks like he's charging, well, it looks like someplace between $35 and $40. And when he charges 8 cars, it looks like he's charging $60. So one way to think about it is the ratio between the number of cars he's washing and the dollars, it stays at 2 to 15. Notice 2 cars for every $15, or I guess I could say $15 for every 2 cars. And so when you go to 8 cars, you're multiplying by 4 the number of cars, and you're also multiplying by 4 the number of dollars. So once again, since we have a fixed ratio here, all 3 of these points sit on the same line. But then they ask us down here, they say, how much does Drew charge for 4 cars? Well, if it's $15 for 2 cars, well then 4 cars would be twice as much. So it would be $30 for 4 cars. We have the same ratio. Let's do one more example. Here we're told McKenna earns money each time she shovels snow for her neighbors, as she should. McKenna plots points on the coordinate plane below to show how much she earns for different numbers of times she shovels snow. All right, so let's see. When she shovels snow 3 times, looks like she gets halfway between 16 and 20. Looks like she gets $18. 4 times, looks like it's $24. So it looks like the ratio is staying constant at 3 to 18. The ratio of 3 to 18 is the same thing as, or one way to think about it is $18 for every 3 times she shovels snow. That would be equivalent to $6 for every time she shovels snow. So let's go down here to see what they're asking us. They say, which of the following ordered pairs could McKenna add to the graph? So this would be 1 time shoveling snow, would she get $10 for? So does she get $10 for every time she shovels snow? No, that wouldn't be consistent with the data here. She got $18 for shoveling snow 3 times. So that looks like she's getting $6 for every time she shovels snow. So I would rule out choice A. Choice B, shoveling snow twice, she gets $12. Well, that makes sense. If she gets $6 every time she shovels snow, the ratio of shoveling of the times to the dollars is 3 to 18, or 1 to 6. That would be equivalent to 2 to 12. And we would
okay, I start to feel like this is too simple. How about the rates? Rates is another idea. It's related to speed. You know, how quick a thing could be, or how quick a change would be. Let's get into the introduction of the rates.
What I want to explore in this video is the notion of a rate. So let's look at some examples of rates that you've probably encountered in your everyday life. So if you're driving in your car down the road and you're looking at the speedometer, you might see that it says that you are going 35 mph, where the mph stands for 35 miles per hour. Well, what's that saying? That's saying, well, every hour, how many miles are you going if you were to stay at that current rate? So it could be a measure of speed. How much distance are you covering per unit time? And most typically when people talk about rates, that's what they're talking about. They're talking about how much of something that is happening per unit time. And it doesn't have to be even distance per unit time. You might have your hourly rate for someone who's doing some type of a job. They might say that they're making $10. So they're making $10, and actually, let me write the dollars out so the units become a little bit more obvious. $10 per hour. Dollars per hour. And so once again, this is how much money, it's not talking about distance anymore, how much money is being earned per unit time. And so even though rates are often associated with how much something is happening per some unit time, and it could be miles per hour, or it could be meters per second, or in this case, it could be your wage, it could be dollars per hour, rates don't have to be just in those terms. In fact, you might say, all right, I have a dessert that I really enjoy, but I'm very conscientious about the number of calories that I consume. And you might see something like there are 200 calories per serving. And so this is telling us the number of calories per a serving. And they'll tell us what a serving is. A serving might be a cup or 8 ounces or whatever else. And so I could say, okay, look, if I have 2 servings, then I'm going to have 400 calories. Same way if I work 2 hours, I'm going to have $20. If I go 2 hours, I'm going to go 70 miles. So rates give you a sense. It's like how fast is something happening, or how much of one thing is happening for every time something else happens. Now I can write rates so they look an awful lot like a ratio. And these words are actually very related, because you see that even how they're written. RAT. Their roots are coming from the exact same idea. In fact, this rate over here, 35 miles per hour, it could come from, hey, I just went 35 miles in 1 hour. What's the ratio? So the ratio of miles to hours. And then you could say, well, if I went 35, it's the ratio of miles to hours was 35 to 1. Or it could have been, maybe it was 70 to 2 or something like that, but that could have been reduced to 35 to 1. So as a ratio, you would typically see it written like this, or maybe see it written like this. And sometimes you might even see it written like this, 35 miles to 1 hour. But now it's starting to resemble more of the special case of a ratio, which we call a rate, because this is the same thing as 35. Instead of writing it out miles per hour, you'll often see it written like this, miles per hour. So these are very, very related ideas. If you find the ratio between calories and servings, well, then you're going to be able to write, you are going to be able to express it as a rate, and vice versa. Now, why do we care about rates? Well, especially if we're thinking about things like speed, without rates, it'd be hard to quantify how fast things are happening. Otherwise, we'd be in a world where we're saying, hey, I'm faster than you, or she's faster than me, but we wouldn't be able to quantify exactly how fast they are. But with rates, we can say, hey, that person ran 100 meters in 10 seconds. They run 10 meters per second. We can quantify exactly how fast that thing is happening, the rate at which it is happening. Here, instead of saying, hey, a cup of that is going to give you more energy, or or maybe contribute more to your weight than a cup of that, and making these relative comparisons, here you can actually quantify things. And when we study rate, we're going to study rate a lot in mathematics. It's going to be essential in algebra when we look at the rate of change of a line, how far it moves in the vertical direction relative to the horizontal direction. We're going to call that slope. And you could even imagine a slope of a hill is kind of how fast is it climbing for as much as you move forward. But we're also going to study rates in detail when we go to calculus. In fact, the whole basis of differential calculus that you might see later in high school and early college is all about measuring instantaneous rate. How fast is something going right now? So rates are really, really interesting, really, really important. And I would guess that if you just look around your life, even over the next few hours, you're going to encounter many, many, many rates.
Okay, good explanation for the rates. So for the rates, it has some relationship with ratio. Basically, they are the same thing as far as I say now. Here's another idea called percent. This is also a very common used mathematical item that we would use in real life.
We're asked to shade 20% of the square below. And before doing that, let's just even think about what percent means. So let me just rewrite it. 20% is equal to 20. I'm just writing it out as a word. 20%, which literally means 20%. Let me break it out, which is the same thing as 20%. And if you're familiar with the word century, you might already know that this cent comes from the Latin for the word 100. So this literally means this literally means you can take cent, and that literally means 100. So this is the same thing as 20 per 100. 20 per 100. 20% means you're really going to, if we want to shade 20%, that means we want to shade, if you break up the square into 100 pieces, we want to shade 20 of them. 20 per 100. So how many squares have they drawn here? So we go horizontally right here. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 squares. If we go vertically, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is a 10 by 10 square. So it has 100 squares here. So if we want to shade this, or another way to say it is that this larger square, I guess that's the square that they're talking about, this larger square is broken up into 100 smaller squares. So it's already broken up into the 100. So if we want to shade 20% of that, we need to shade 20 of every 100 squares that it is broken into. So in this, we'll just literally shade in 20 squares. So let me just do one. So if I just do one square just like that, I have just shaded 1 per 100 of the squares. 100 out of 100 would be the whole. I've shaved one of them. This would be, that one square by itself would be 1% of the entire square. If I were to shade another one, if I were to shade that and that, then those two combined, that's 2% of the entire square. It's literally 2 per 100, where 100 would be the entire square. So if we wanted to do 20, we do 1, 2, 3, 4. Actually, if we shave this, if we shade this entire row, that will be 10%, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we want to do 20, so that'll be one more row. So I can shade in this whole other row right here. And then I would have shaded in 20 of the 100 squares. Or another way of thinking about it, if you take this larger square, divide it into 100 equal pieces, I've shaded in 100, or I've shaded in 20 per 100, or 20% of the entire square. Hopefully the entire larger square. Hopefully that makes sense.
Okay, so the percent is a special case on the 100 base rates. If I'm the one who explain it, that will be this percent means x over 100, and that's it. One thing to mention is that we could actually convert those ideas around. For example, now if we have a number called 0.6, this is a float number, and it's also as we have learned before, it's also a decimal. And how do we convert it to a fraction? Oh, maybe that's not appropriate. Let's say, oh, it's appropriate. We could convert it to a fraction, which is 6 over 10, and they have the same value. We could also convert it to a percent as long as we ham it by 100, and this is a percent. Here's another section called Constant of Proportionality. What is that? To be honest, I don't know. So let's get into it.
We're asked, what is the constant of proportionality between y and x in the... And just as a reminder, when we're talking about constant of proportionality, it sounds like a very fancy thing, but it's not too bad. If we're thinking about any xy pair on this line, let's say right over here, we have some x comma y. If y is proportionate or is proportional to x, then that means we can say that y is equal to some constant. Y is equal to some constant times x. And that constant, that is our constant of proportionality right over there. Sometimes you will see this expressed if you divide both sides by x. Sometimes you will see this as y over is equal to the constant of proportionality. It shows for any xy pair, if you take your y divided by x, what do you get? That's the same thing. So with that out of the way, see if you can answer their question. What is the constant proportionality between y and x in the... Well, they very clearly give us a point right over here. This point is the point 3, comma 2. And so we could set it up a few ways. We could say, look, when y is equal to 2, x is equal to 3. And so 2 would need to be equal to some constant of proportionality times 3. If you wanted to solve for this, you just divide both sides by the 3. Divide both sides by 3, and you would get that your constant of proportionality is 2/3. Another way to do it, right over here, well, here we've kind of already solved for a constant. When y, or we could say when x is 3, y is equal to 2. In either case, our constant of proportionality is 2/3. Let's do another. So here we have which line has a constant of proportionality between y and x 5 over. So pause the video and see if you can figure that out. So the key realization is we should test points on these lines. We should test xy pairs and say, well, look, if we take our y divided by x, do we get 5/4? Because that would be our constant of proportionality. So let's first try line A right over here. The line A, let me find a point that sits on it. So that point on it. And so if I take, this is the point 2, 5. And so if I took y divided by x, I would get a constant of proportionality as 5 halves. So A is not going to be our answer. We want to get to a constantality of 5/4. All right, let's try B. Okay, B, let me find a point on B. Looks like this is a point on B. That is the point 4, 5. 4, 5. So in this situation, K would be our y, which is 5, divided by our x, which is 4. So it looks like B is our choice. Kicks, you could also look at the constant of proportion. Now there is one interesting example that I just want to touch on before we finish. What about a situation where y is equal to x? What is the constant of proportionality then? And what would it look like as a line? Pause this video and think, well, there's really nothing new here. It's just you might not really see the constant of proportionality when you see it expressed. But y is equal to x is the same thing as y is equal to 1 times. And so then it might jump out at you that the constant of proportionality is 1 in an area right over here. Or if you took y divided by x, y over black color, or if you took y over x, you divided both sides by x, you would be left with the constant of proportionality equal to 1. And if you wanted to graph it, well, it would just look like this. Y would be equal to x for all x. So that's what, when your constant of proportionality is 1, those would represent points on this orange line that I...
Alright, so let's say in the last video, we have learned about the concept of constant of proportionality. Nice, let's go to another video.
What I want to introduce you to in this video is the notion of a proportional relationship. And a proportional relationship between two variables is just a relationship where the ratio between the two variables is always going to be the same thing. So let's look at an example of that. So let's just say that we want to think about the relationship between x and y. And let's say that when x is 1, y is 3. And then when x is 2, y is 6. And when x is 9, y is 27. Now this is a proportional relationship. Why is that? Because the ratio between y and x is always the same thing. And actually the ratio between y and x, or you could say the ratio between x and y is always the same thing. So for example, if we say the ratio y over x, this is always equal to, it could be 3 over 1, which is just 3. It could be 6 over 2, which is also just 3. It could be 27 over 9, which is also just 3. So we see that y over x is always going to be equal to 3, or at least in this table right over here. And so, or at least based on the data points we've just seen. So based on this, it looks like that we have a proportional relationship between y and x. So this one right over here is proportional. So given that, what's an example of relationships that are not proportional? Well, those are fairly easy to construct. So let's say we had, I'll do it with two different variables. So let's say we have A and B. And let's say when A is 1, B is 3. And when A is 2, B is 6. And when A is 10, B is 35. So here, you might say, oh, look, when A is 1, B is 3. So the ratio for the ratio B to A, you could say B to A, you could say, well, it's when B is 3, A is 1. Or when A is 1, B is 3. So 3 to 1. And that's also the case when B is 6, A is 2, or when A is 2, B is 6, 6 to 2. So these ratios seem to be the same. They're both 3. But then all of a sudden the ratio is different right over here. This is not equal to 35 over 10. This is not equal to 35 over 10. So this is not a proportional relationship. In order to be proportional, the ratio between the two variables always has to be the same. So this right over here, this is not proportional, not proportional. So the key in identifying a proportional relationship is look at the different values that the variables take on when one variable is one value, and then what does the other variable become, and then take the ratio between them. Here we took the ratio y to x, and you see y to x, or y divided by x, the ratio of y to x is always going to be the same here, so this is proportional. And you could have actually gone the other way. You could have said, well, what's the ratio of x to y? X to y. Well, over here it would be 1 to 3, which is the same thing as 2 to 6, which is the same thing as 9 to 27. When you take this ratio, if you say the ratio of x to y instead of y to x, you see that it's always 1/3. But any way you look at it, the ratio between these two variables, if you say y to x, it's always going to be 3, or x to y is always going to be 1/3. So this is proportional while this one is not.
Okay, good explanation on the concept of proportional relationship.
Proportional relationship.
Proportional relationships. Yeah, that makes sense. Two things always have the same rate or always have the same ratio. Okay, I guess that's today's learning, and let's say today we have learned the concept of ratios, rates, and proportions. Those things are indeed the basics of the algebra, and that's why in here they call the whole lessons on this page the pre-algebra, because it's just an, let's say, preparation for you to get started to learn the algebra. And we are almost done. We just need 2 more learning day to be able to get started with algebra learning, and in there will be learn a lot of more interesting things. Okay, that's today's learning for mathematics, and I'll see you guys in the next video. Bye.